All right, so welcome everybody to the first theory seminar of the winter quarter, and as is our tradition, we have a local economist speaking, and so today I'm very happy to introduce Mark Sattherwaite, and I guess I should also thank our sponsors. Do we still have, Yahoo is sponsoring our lunches, and I don't know what the video talk recording, no?
They're no longer sponsoring our video.
But we're still very happy to be able to record the talks. So Mark will talk to us today about optimality versus practicality in market design. Thank you.
Okay, thank you very much, Nicole. I always feel it's very strange to be invited to a computer science department to teach, to talk. I took exactly one computer science course as an undergraduate, and I took it for the worst of all reasons. I had to complete a math requirement. But it was a good thing. It was Donald Knuth, long before he was, well, not long, because he got famous very fast. But anyway, I actually learned a lot from it and affected a lot of what I've done since then. But anyway, I want to talk about this paper, Optimality versus Practicality in Market Design. And it's joint with Steve Williams, who we've written many papers with at University of Illinois, and Kostas Zacharidis, who's at LSE and was a PhD student in the MEDS program. So, what's this paper about? Gee, you know, it's sort of when it wants to talk about, with an example and some results, the usefulness of mechanism design versus just plain analyzing equilibrium behavior of particular practical mechanisms. And so, you know, here's a real fast history. You know, Vickery started the whole thing with his second price auction, famous second price auction paper, which sat for a long time with none of us reading it and doing anything about it. But that was, of course, an independent private values market, and we got you know, the famous theorems about revenue equivalent. This is optimal in a certain sense. It's got the revenue equivalence, though it doesn't have, I don't think, reservation values. Then Meyerson came along in '81 in a paper which really, I think, won the Nobel Prize for him in inventing mechanism design. And as an aside in that paper, he said, gee, if you had correlated private values, he didn't call it that, you could do better by exploiting that correlation. You can actually fully extract surplus with an auction. And then Kramer and McLean in 1988, you know, really did that in the auction context in a more general way and in a more modern language. Now, you know, auctions, what are auctions? They're when, you know, a seller doesn't know what, how other people value the good, and he's just going to use the mechanism to extract those values. So it's got one-sided, incomplete information. In an auction, you want to sell it, and I just want to get the best price. I may set a reservation price, but that's generally a public thing. I just don't know what you want. In a double auction, it's two-sided incomplete information. I want to sell you something, but you don't know what its value to me, and if you don't value it enough, I won't want to sell it to you. You know, I may like it more than you like it. And so, you know, so Roger and I wrote a paper in '83 which showed that you couldn't extract full surplus with independent private values in a simple double auction, and that was, you know, a general result. And then McAfee and Rennie in '92 said, gee, you know, these ideas of Roger and Kramer and McLean can be applied to this, and you really can extract full surplus by an appropriate auction design. And so we're going to build off this paper here. Now, why do, you know, given these great results, you know, you can get perfect efficiency and all that, why do we study the first price, English, second price, Dutch auctions? I'm going to talk about buyer's bid double auctions on the double auction side. Well, gee, there's a number of things. This is the Wilson critique, which is pretty devastating. Gee, how the, you know, I'm going to design a mechanism so we can all trade efficiently, and I'm going to write down as my first step a common knowledge prior that I can calculate with. I have no idea how you value this pointer. You know, you just can't do it as a practical matter. It's absurd. and then there's the timing of the constraints. A lot of these mechanism designs don't protect you against ex post rationality. You may regret you participated. Of course, sometimes that happens. And ex post budget imbalance, gee, the Chicago Board of Trade goes bankrupt because they had ex post budget imbalance. Very unlucky for 6 months in a row. And then moreover, magnitude of transfers can get very large. In fact, in the Kramer-McLean situations, as you approach independence from correlated values, those necessary transfers blow up to infinity. And paying out that kind of money causes problems as a practicality. So people have also studied these, which have ex post budget imbalance, that have ex post individual rationality. And gee, they aren't perfect, they aren't efficient necessarily, so sometimes they are under some circumstances, and so on. So here's what I want to do in today's talk. I want to compare two mechanisms for trading with two-sided incomplete information. In other words, some Myerson and Sattherwaite setup, but not independent values, but correlated private values. And so the first one is buyer's bid double auction. This is, like an English auction or a Dutch auction. It's an obvious common mechanism, which is basically supply and demand. And I and colleagues and others have shown that, gee, in independent private values and also in correlated private values, you get a really rapid convergence to efficiency. I'll give you a numerical example at the end that just underlines that, as well as some results on that. And, so there were a bunch of papers in independent private values and encryption Schwinkels, as well as Freudenberg, Mobius, and Seidel had some papers on correlated private values. And I think the bottom line on that is, first, existence is kind of hard as soon as you put correlated private values on it. But second, if you do have existence, boy, it behaves just like independent private values, the rapid convergence to efficiency. Now, the design mechanism that I'm going to create for this setting of multilateral trade is just based on the McAfee-Rennie construction for correlated private values. In some ways, it's not a very, technically, I don't think it's a great thing. The real innovation here is going to be the model that we use. The wonderful thing about the design mechanism I'm going to show, it's going to be first best efficient. In other words, we're going to realize all gains from trade. Of course, incentive compatible. Everybody's going to review ex ante individual rational. Notice, not ex post individual rational. You want to participate, but you may be regretful afterwards. And ex ante budget balance. So if you keep playing it long enough, you break even. But you could have a bad run of luck. So I want to talk about what are each mechanism's flaws, and I think very important, do they go away as market size increases? And so, what are the properties of these two mechanisms? Just a preview. Well, gee, if you play something like the buyer's bid double auction, I'm going to define it in a second, you've got to compute an optimal bid. And quite truthfully, that's not necessarily easy. And then the strategic bidding by traders ends up making it inefficient. That there are some gains from trade that are not realized. But as the market size increases, pretty soon you might as well truthfully report, and that's almost optimal, and it becomes almost efficient. And all this happens very fast, the convergence. And this is true in independent private values, it's true in correlated private values, and it appears to be true in interdependent correlated values. And the design mechanism, the Wilson critique is going to apply. We're going to have ex post individually rational, at least sometimes, depending on underlying distribution. But it's always, under some cases, going to be ex post budget imbalance. And these flaws do not go away as the market increases in size. Now, at the end of the talk, I hope I'll have time to say a conjecture, which says, gee, you can't do better than this, no mechanism. This would be a particular mechanism that we have designed here, and so it's not a perfectly general result here. Maybe you could do better. Maybe you could get rid of the this part, which I think is most serious type of thing. Okay, so here's our model, and this model is a little bit different. We've got M buyers, each wanting one item, and M sellers, each with one item to sell. So I'm just going to work with, balanced markets. Not that I think that's particularly important. It just keeps notation easy and everything else. And so buyer's utility is going to be, if he gets the object, it's his valuation plus whatever money he receives. Now that's usually going to be a negative number, obviously. He's going to buy it. And seller J's utility will be whatever money he receives, which usually would be what he received, minus whatever his cost is. And so it's the V and the C, which are private information to each. Now these are the valuations of buyers and the valuations, the costs of sellers are going to be correlated in a way that I'm going to indicate in the next slide, I believe. Yes. So here's how we construct, in this case, the model with the correlated values. First, it's going to be an unobserved state. Nobody's going to observe this state. And it's going to be a state mu, and it's going to be distributed according to a diffuse prior on all of R. In other words, you know nothing. It could be any place. And, there's a history in Bayesian statistics and decision theory in which they use this. And, gee, it actually works pretty well. It's not as extreme as it seems in practice. At least that's my reading of that literature. And then each trader is going to draw, again, unobserved, an epsilon I that is independently drawing from F on R. Let's say an example I'm going to use is a normal distribution. And make it standard normal. And then that's basically noise on mu that gives you your private valuation or your private cost, just additively. And this diffuse prior basically says we've got complete ignorance. And when you get your valuation, when you realize your valuation of cost, you have no idea whether you're high or low. Now, whenever we do the standard model, which simply is the one that I've mostly used in my career, we draw these things from 0 to 1. And key, when I see a 1, and I'm a buyer, I know I'm strong. But here, there's none of this. And so it's going to create a lot of symmetry, which is awfully useful technically. And I don't think it does very much damage. Okay. And so interim trader is going to have a proper prior on mu, and therefore a proper posterior on mu, and therefore, since he knows how other people's costs and values are created, he's going to have a proper posterior on the values and costs of the other 2m minus 1 traders. And so you can do decision theory on that and decide what your best bid is. And of course, this is going to have a lot of correlation between all the values and costs just generated by that mu being shared by everybody. They're all going to be close together. So here's, gee, this isn't very good, but I'll try to trace it out. Mu is uniform on the real line. So it could be any place you could be. Mu could be minus 10 million or plus 10 to the 6, but let's suppose it comes out to be 72, a more tractable number. So right here, and then my valuation, once I have my valuation, will be, let's say, normally distributed around 72. And, so it could be, 74, it could be 70, but it's unlikely to be 0 if it's normal 0, 1 noise on it. So, I suddenly have a good idea about where mu is. Because after all, if you do the appropriate Bayes rule, you're going to have that your posterior is going on mu is going to be normal 0, 1 about 70. About 76 if I drew 76 as my cost. So I know a lot. And then once I have this, gee, I know how your values were done. And so it turns out for a given one, leaving out the correlation structure for a second, it'd be your value would be or cost would be distributed standard normal 72 with variance 2, mean 76, variance 2. And so I know a lot about your valuations, but notice everything's symmetric around my draw of 76 for me. Now, gee, would anything important change if I draw in 212 as my value? No, I get exactly the same picture. I have all the same symmetry. I wouldn't know whether it was high or low. You know, it's just a translation. Nothing changes. Now, if nothing's really changed except the translation, what do you think is going to happen to my strategy? Well, my strategy shouldn't really change either. And what we're going to get in all these, both mechanisms that we look like, is strategies will be essentially offsets from your value. And nothing will change. So if I get a 76, and it's best for me, and I'm the buyer, and it's best for me to bid, to misrepresent, by down to 75 when I bid. Well, gee, if I draw in a 201, then I'd offset -1 and go down to 200 in my bid. It's gone, you know. And gee, that's enormously useful. Instead of strategies being a function, which I have to derive, it's a number. And gee, numbers are a lot easier than functions. Okay? Any questions? This is I think, the neatest part, actually.
This distributional assumption?
This could be a general, pretty general F.
So with the diffuse prior, it seems like it's a setting where Kramer-McLean, for instance, doesn't have any bite.
I haven't thought seriously about it, but it has a lot of bite here. I mean, we're going to be able to do the same thing.
Kramer-McLean is trying to extract full surplus, or the McAfee-Rennie is trying to get full welfare.
We're going to do the same thing. The same result. Doesn't matter.
But I guess my point is, I don't think they would.
Well, gee, they'd have to change their analysis. I think they get the same thing. Think about it. You know, I think this is just a natural generalization, using a different distribution than they did, and just.
But so the Kramer-McLean needs the distribution to have some kind of non-genericity.
Yes.
I think
that's true.
Genericity.
And I think that probably applies here, though I haven't checked it. Okay. The fact that we get full surplus makes me very suspicious it applies. Full surplus extraction makes me very suspicious. Exactly the appropriate generalization applies. Okay. Now, I may say a word or two further along. Okay. So we're going to compare buyer's bid double auction. Let me briefly go over that. And, so you simultaneously solicit a bid from every buyer and an offer from every seller. Order them from lowest to highest. And in the generic case, you'll have no ties since we've got continuous distribution. And, and so given that we've got M buyers and M sellers, the market clearing price is going to be in the interval from SM to SM plus 1. And so supply and demand will be balanced at any price in this interval. And I'll show you a picture in a second, and it may help a little bit. And in the case of the buyer's bid double auction, we're just going to set the price at the top end. Got to be a little bit careful about ties and so on. I'm not going to be careful here. And now, by doing this, setting price at the top end of this interval, it's going to mean that the dominant strategy for strategies for sellers is to reveal honestly, because you can't affect the price. And you can see this in here. Now, here's an example of M equals 3. Here's the buyer with the highest value. Then there's buyer with the second highest value, buyer with the lowest value, supply going up like this. And so where's our interval of market clearing prices? One item is going to sell. It's right in here. And so I'm saying set the price here turns out a seller sets that price. So this seller who's setting the price, that's S, the fourth order statistic going up. Well, why, if he's setting the price, why doesn't he want to manipulate it? This guy isn't trading when he sets that price. So it doesn't matter. And, this seller down here certainly didn't affect the price. The sellers can't affect the price. Of course, buyers can affect the price. I could have just switched this around a little bit and demonstrated that. So they, of course, are going to try to manipulate that price, and will have an incentive to underbid. Okay, so, so it's just a simple implementation of supply and demand in a static setting. Okay, here's some equilibrium results that, one gets. Now, in an offset equilibrium, there may be other equilibriums, we aren't sure. A buyer's strategy is to bid for whatever their value is. There'll be some offset for lambda, which will be a positive number. You want to underbid. So how much you want to underbid doesn't matter on your valuation. It's just, a property that comes from the underlying distribution of F and the fact that things are drawn from the diffuse prior. And I'm going to use normal 0, 1 to, because it's convenient computationally to make example. Now, does an equilibrium exist? Certainly does in this case, though the standard ways that we prove existence do not work. And when you go through it, it's perfectly apparent why they do not work. Affiliation just doesn't work in this setting, and in general, it doesn't work in double auctions. Now, so how can I assert that an equilibrium exists? Well, basically because we're working with a number, and so it's very easy to check numerically along a line that this maximizes. And, but there's other distributions. What is it? Well, for example, it works with the Cauchy, which is a badly behaved distribution. You still get existence at least when you've got two or more buyers and sellers, each m equals 2 or greater. So and what happens as m increases? Well, lambda goes down linearly, and then the relative inefficiency goes down quadratically. Now, what do I mean by relative inefficiency? Suppose everybody, counterfactually, reveal their true values. Then we get complete efficiency, true values and costs, and that'll give a certain ex-ante gains from trade. But of course, buyers do not do that. They underbid. That causes certain trades not to be realized, and so we get a smaller gains from trade. So gains from trade first best minus gains from trade equilibrium, that gives lost ex-ante gains from trade divided by gains from trade. So you have it as a proportion, and that goes to 0 quadratically. Why is it quadratically? Well, it just follows directly from this. I haven't drawn the triangle, but as you've got a supply and demand like that, and as you're cutting it off over here and pulling it towards the thing, the area of that triangle goes away. It's known in economics as the Harburger triangle. And that's, so if you have that relatively easily implies this quadratic convergence. So as m goes to infinity, you're going to truthfully reveal, and we're going to get full efficiency. The performance becomes first best as m goes to infinity. Questions? Okay. Basic designed mechanism. So first I'm going to create I'm going to do this in 2 steps. First, a basic mechanism where buyers will get absolutely nothing. They'll just have interim they'll have interim utility of 0, ex-ante expected utility of 0. Then we're going to distribute some extra gains from trade, which the mechanism operator has been collecting, to buyers, and see how well we can do. So we do first basic design mechanism that understands sort of the incentives, and then we'll see whether we can correct some of the problems of that. And we won't be able to correct them as well as we would like. So what will our basic design mechanism consist of? Well, gee, we'll have incentive compatibility, so we'll have a Bayesian Nash equilibrium, and it'll be a dominant strategy. I'm not sure it'll be a dominant strategy. Anyway, it's a Nash equilibrium. That's something I had to work out. I meant to cross out that word. So here's the sentence that I mean. Honest reporting by each buyer defines a Bayesian Nash equilibrium. And in equilibrium, it's going to be efficient. In other words, no gains from trade will be left on the table. Either the mechanism operator or the sellers is going to are going to get it. But buyer's interim and expected utility will equal 0, and that'll just help in the derivation. And all ex-ante gains from trade, therefore, go to the sellers and to the mechanism operator. So, how do we get that? Well, gee, it's a double auction type of thing, and it's static, no time involved. So buyers and sellers are going to simultaneously report their values and costs. Now, they don't have to report their true ones, but it's going to be equilibrium for them to do it. So I'm not going to dwell on that in the notation or the discussion. The trades between buyers whose report, and then what will we do? Well, gee, we've got the values and the costs, so we'll just assign the objects to the right people. So it'll be efficient. We'll put so the trades will be between buyers whose reports are among the M largest and the sellers whose reports are among the M smallest. And that all adds up because we've got the even number of things. We've got supply and demand equals here. And then we'll, just like in the buyer's bid double auction, we're going to pay each seller after we order these values and costs, we're going to sell them the M plus, we're going to give them a price, which is the M plus first order statistics when we've arrayed them from lowest to the highest. In other words, we're doing exactly what we did in the buyer's bid double auction, and this, of course, will induce dominant strategy, honest reporting, because they can't affect the price they get. Then, and the important part is, we're going to solve for the buyer's payment. So it's incentive compatible. He maximizes his interim expected utility. After all, he does, he knows his value, so he's going to figure out what he wants to report. And he'll want to report honestly. He wants to report his true values. And we'll do it and we'll provide these incentives in a way so that his interim expected utility is 0. In other words, he neither expects to come out ahead, nor worse, low ex post. He might come out a bit ahead or a bit behind. Maybe quite a bit one way or another. Okay. So that's the basic pattern. Yes.
So this is not necessarily budget balanced. It is not necessarily budget balanced.
It is. I'll talk about budget balance extensively. No, this is not necessarily budget balanced. And in general, it is not budget balanced, and I don't talk about that. Okay. Now, how do we set up this mechanism? I'm going to go through it. It's actually pretty simple, but I'm not going to go through it so you could replicate it. I mean, I've sat on that side of the table, but I'll give you an idea that it's not the hardest thing. And I might say the reason why, one of the things that really makes it easier is, remember, just like in the buyer's bid double auction, we're basically going to be solving for a number. It's all that symmetry we get out of that diffuse prior setup. Now, suppose buyer I with value V reports I trades if and only if his report is greater than the nth order statistics. In other words, he's among the top M, and then he's going to pay the mechanism. He's going to pay the mechanism operator minus alpha M if R is less than SM. Well, turns out, and quite truthfully, as I prepared this, I decided our notation is terrible here, and it's confusing, and I spent an hour trying to convince myself it wasn't wrong. You probably had that happen to you, but anyway. Jason, you're thinking something. It's not ready for publication. If this was an auction, you just bought an artwork that you did not want because your finger went up. Okay. Okay.
I had a question earlier and I raised my entire hand.
Okay, now I know. We've now agreed on it. And you
so
can.
I figured that raising my finger was fair game, and that was a less.
It caught my eye.
Gesture.
Okay, but anyway, and so it turns out alpha is going to be a negative number, and so he's going to pay. So if he doesn't trade, he's going to pay minus alpha m, which is a positive number. So he's really going to pay something if he doesn't trade. And and if he and beta will also be a positive number, and so he's going to pay whatever he reports, which is going to be the truth, plus a negative number plus a positive number if he does trade. Turns out this is sufficiently general, and it's not great cleverness on our part. We're basically copying the approach that McAfee and Rennie followed. And, then his minimum expected utility, if you work it out, is just alpha plus V minus R minus beta times the probability he trades. And zero intermittent utility says, gee, it's just UVV, given the size of the market, should equal this 0. And that's going to imply that alpha equals beta times the probability of trading. Now remember, the market's of equal number of buyers and sellers, and given our assumption of diffuse prior, it's going to mean in equilibrium, you're going to have a 50% probability of trading. And that's just because you never know whether you're high or low, so you're equally likely to be high or low in it, and that's going to lead you to have a 50% probability of trading. Anyway, you can prove that if you don't like the intuition. And then you can take the first order condition with respect to R, but it turns out it's inconvenient to do it with R. It's better to differentiate with respect to V, and it turns out you can get away with that because UVV equals 0, and and if UVV equals 0, there's interim expected utility, then differentiated by R just equals negative of differentiating by V, and that's very easy to see, and that's going to allow us to solve for beta Rm.
So for your third bullet, that probability term, that's just some constant.
It's going to be a constant.
Because
correct.
You have this diffuse prior, right?
Absolutely correct.
So
and that really, really helps. And it's going to, so these betas actually are not going to vary. Beta and alpha are not going to vary with respect to R.
And so, the Kramer-McLean intuition, I believe, is you have the agents bet against each other based on what they think the prior is.
Yes,
So
that's
if you have
correct.
a diffuse prior, maybe you think that your value is centered in that diffuse prior, and so the agents
Yeah, I think
differ in their belief on the prior, and so you have them bet with respect to this, are they balanced with SM?
And because of all the symmetry, it becomes kind of trivial here.
Right.
And gee, I think that's awfully nice. You may think your taste may say, gee, that's terrible too. I can understand looking at it both ways. Okay, but your intuition, I agree with what you just said. Okay, so given that mu is diffuse, and that you have those constructions of the values and costs, that is going to imply, and we prove it, that this probability is a constant of 1/2, and that this derivative is negative and invariant with respect to v, your v. Just, so in other words, it's just going to be constant throughout. And so, given honest reporting, and that's a Bayes-Nash equilibrium, the buyer's payment is, if he doesn't trade, is negative alpha m. That's a payment to the mechanism designer. You didn't trade, but give me money. So that's ex post individually irrational. But if you do trade, you still have to pay that, but you're going to get the beta, which is where, has a different sign from the mechanism designer. And, so because of this 1/2, beta is, beta is just twice alpha. You're going to get your value, you're going to pay your valuation plus beta minus alpha. Well, that turns out to simplify to v plus alpha, but alpha is a negative number, so you're going to pay less than your valuation, which is what you want when you're a buyer. You're underbidding there. And why do you have interim? Why do you have interim utility of 0? Well, you come out ahead when you trade. You come out behind when you don't trade, and it all balances out. And you can actually see this. You come out this much behind with probability of 0.5. This much the same amount ahead with probability of 0.5. So it's the 0. Now, a buyer suffers an ex post loss when he fails to trade, and it's just this this negative number. This is a negative number because this derivative is negative, and this loss occurs with probability 1/2 in our monitor, and it doesn't vanish as m increases. And in fact, as you look at this asymptotically, it goes to this value, minus 1/4 times the value. Remember, f was what those epsilons were drawing from, and the value of the density right at the median. G, depending on what variances you choose and so on, you can make this number as big as you want. So this could be a pretty big number. In other words, when you trade in this mechanism, you darn well better not be risk averse, because if you are, you might run the other direction. And rightly so. Any questions about that? But so this loss, that's just part of the game of playing in it. That can become a big name, big number. So in that sense, it's just like Cremier and McLean. And I think if I thought about it a little while as you make suppose you have a normal, F is a normal distribution, then you make the variance bigger. Well, gee, I think probably in a well-defined sense, you're going from less correlated, as you make the variance bigger, you're going from a more correlated to a less correlated situation. And so your payments explode as the variance goes to infinity. That's exactly what this what says, and it's exactly as in the case of Kramer-McLean, where as you go towards independence, the payments explode. Okay, what about the ex-ante of budget surplus? Well, gee, in the basic design mechanism, we've got the buyers ex-ante break even, and so the gains for trade, GFT, remember, it's the ex-ante gains from trade that buyers and sellers expect in aggregate. They report their values and costs honestly, and then we just do the buyer's bid double auction. So that's, that's what we should get in efficiency. Well, gee, in the basic design mechanism, we are doing that. We're basically doing it on the seller side, but on the buyer side, we're ex-ante giving them, and an expected value, we're giving them nothing. So essentially, you know, if everything's symmetric, the mechanism operator is keeping half this. So there's a lot of, we've got a chunk of money, you know, the sellers have gotten what they should get right off, but buyers have gotten nothing in expectation here. Okay, well, gee, you know, so that's what I said. Now, this difference, we've got a lump of money which we can then distribute as lump sums. So if what we might do is to say, gee, we don't like buyers. That's exactly what we're going to do. They have all this ex post irrationality. So why don't we just give buyers a lump sum? Use this money and split it evenly among buyers. Give each buyer this lump sum to offset those payments if they don't trade. And that's going to be a designed mechanism. So that's, here's the setup. Convert the basic design mechanism to an ex-ante budget balance mechanism by distributing as a lump sum to each buyer an equal share of its ex-ante, of the basic design mechanism's ex-ante budget surplus. That's what we had in the basic design one. Sellers came out fine, but we kept that half which really belonged to sellers, to buyers. Now we're going to distribute to each one this gamma lump sum. Now, you know, lump sum distributions have no effect on incentives. You always get it. So you can act silly, you can optimize, but if you do optimize, you get the same answer. Now the asymptotic value of this lump sum is a very simple expression. Remember, x1 half, well, I don't know where, x1 half is just the median of f. So if you're using the standard normal, this is just 0. And so this is just the expected value of the right-hand tail here of f. And so depending on f, this asymptotic ex post utility of a buyer who does not trade may or may not be positive. What is that asymptotic ex post utility? Well, it's just a lump sum minus that expected expected ex post irrationality if you didn't trade. That was just this expression. Well, remember, I said this thing works for the Cauchy type of thing. So you can make this infinity if you want. You'd have no ex post irrationality then. Though you kind of worry about where you'd always get the money. Occasionally you do real well if you were the mechanism designer. But anyway, this is the design mechanism. You know, now this expression could be positive, though if you pick f as the standard normal, it isn't positive. You know, it is ex post irrational. When you have to put in money when you don't trade. Okay.
The alpha that you pay if you don't trade.
Yeah.
Does that depend on your valuation, on your
No.
reported? No.
No.
So you can
It's
think
just
about
fixed.
it as an ex ante fee.
Yeah. It's like you can think of it as a fee, and that would be the right way to run it.
Okay. And
You
then,
know,
but then
Then
the
you'd have
gamma
nobody
is-
welch if they didn't pay it.
So ex ante they pay a fee,
The alpha,
but they get something from the operator.
then they'll get a lump sum, which might be quite big. You might say, gee, I'll just go. You know, we'll leave that aside. You've decided to do it. You get this lump sum, and then if you don't trade after your review, that's it. You may have come out plus or minus, but if you do trade, then you're going to get additional money. You're going to come out ahead by trading, by successfully buying. You get utility, not additional money. You're actually given more money, but you're given less money than what it's worth to you.
Yes. Okay.
Did I confuse a lot of people, or did I make it straight in the end? Okay, you can stop me if I confused you. So this is the design mechanism, DM. So let's look at that. Now let's look at the worst case ex post budget deficit. Now let me explain to you, and and I think I've got it down. I've got it down so I understand it here in these few lines. But let me see what I can lead you through as to where, how we can get the worst case here. Okay. Now, the design mechanism may run a deficit on an individual trade. So a seller who trades, where it means a deficit is mean that that a buyer may successfully trade, and with a seller, and just on with the seller that buyer is matched out, the mechanism operator will come out negative. He'll pay out more money than he takes in, and I want to show you how that can happen. So think of a pair that are going to be matched, Jason and Lance. Lance is a buyer. Jason is a seller. So Jason always gets SM plus 1 and from the mechanism. Now, a buyer who honestly reviews and trades pays his valuation minus that alpha, excuse me. That's a plus, but alpha is minus. See, I just hate this notation. We'll fix it in the next draft. So he's gonna end up paying this because he trades, where he's paying in less than the thing is worth to him, because plus alpha m is a negative number. So he's paying for the object less than it's worth to him. And then he also receives this lump sum gamma. Therefore, a buyer for whose V equals Sm plus 1, and here I put ties into it. Remember, that's generically impossible here. But we could make it close to it, and it wouldn't change the answer very much. And there's tie-breaking rules and so on if we want to be careful. Now, suppose V equals Sm plus 1, so we just substitute that in. So here's what the buyer would end up paying: Sm plus 1 plus alpha m, that's a negative number, minus gamma n, and that also is a negative number. He's receiving minus gamma m is a positive number. So he receives this big lump sum, and he pays in a little bit here, plus his valuation. But he's making money here, and then receives the lump sum. Now, but this buyer has a value of Sm plus 1. He's trading with a seller, so then the net payment the mechanism receives from the buyer-seller pair is negative, because this is what the buyer receives, and then this is what the buyer pays in, and then minus Sm plus 1 is G. I can't remember who I said the seller was, but anyway, the sellers with which this buyer is matched to, the mechanism has to pay out Sm plus 1. So Sm plus 1 cancels, and so we have alpha m minus gamma n, and alpha m is a negative number, gamma m is a positive number, but it's got a negative sign on it. So what the mechanism is paying out a negative number. And gee, that can be a big number. So in other words, in the worst case, every buyer could have a value of Sm plus 1. Now that's highly unlikely, of course, but m times this difference here is our worst case, and so G, the asymptotic value of the worst case deficit is just m times this. Well, G, that's a terrible number. It just blows up linearly to infinity. It does not go away. Now, this proves, and this is true for any f you pick, where you satisfy some sufficient conditions I haven't talked about. This proves that any mechanism based on the basic design mechanism cannot simultaneously be efficient, incentive compatible, and ex post budget balanced. But what's the key words in there? Based on the basic design mechanism. I don't know, that if we, do something else. I haven't proved that this is a general class, that we can't do any better. I conjecture maybe we can do a little bit better, but I doubt we can do well enough. And I think that'd be a nice thing to prove, that, gee, you just can't get ex post budget balance and keep your efficiency, basically. Now notice in this list of things, I didn't include ex post individual rationality, because for some F's we did have ex post individual rationality. Go back. You're looking down for Jason, where did I? Yeah,
There's a
here.
trick of ISO and
Yeah, here. This could be a positive number, ex post individual rationality. Okay, so that's the basic results. Yes.
There's a trick of ISO and Futo that I've only seen it in the independent case, so I don't know about the correlated case. But
Yeah, there's a trick in what?
of ISO and Futo,
I don't know
Which-
the trick, but
which
probably wish I did.
which takes any mechanism which has some distribution on its revenue. So budget, for instance, budget imbalance is
Yeah.
one of these things, and it replaces it with a deterministic. Like you can have the agents suck up the fluctuation in the
Yeah.
mechanism, and so the mechanism ends up with a deterministic.
Wait, I want to know that trick. And that might be very useful here, if I understand you correctly. And I suspect you told me about it because it might be useful. That'd be neat. Any other comments? Now let me just show you some of the magnitudes of these things. So, let F be standard normal, and then yet let now remember this is the ex post individual irrationality, this column for the design mechanism. These two columns are for the design mechanism. This column is going to be for the BBDA. Next time, if I give this talk again, I'll make a better diagram, table. But anyway, and you can see that, yes, the ex post individual irrationality does decrease as M goes up, but it doesn't go away. But as you can see, exactly as I just said, gee, worst case, budget imbalance explodes. That should be minus infinity as you go. But now look at what happens to the relative inefficiency of the buyer's bid double auction. You've got two people on each side, then you lose 8% of your gains from trade in equilibrium. If you've got 4, you lose a little under 2%. If you've got 8, you lose a little less, about 0.3%. And if you've got 16, you lose 0.06%. In other words, by the time you're at 16, you're losing essentially nothing. It's fully efficient. Everybody essentially is revealing their true values. And of course, you let them go to infinity, everybody does reveal their true values. It's perfect competition. And so this mechanism is, becomes, very quickly first best. These mechanisms are first best as far as efficiency, but they've sort of got these very annoying characteristics which make them hard to use in practice, even leaving out the Wilson critique, which says we can't construct them in a practical way. So where does this leave us? Well, design mechanism, it's flawed by the Wilson critique, at least some of the time ex post irrationality. It's got budget imbalance, ex post, and you can't get rid of them by looking at a big market. The BBDA, simple yet inefficient, but that inefficiency is insignificant even for relatively small markets. So, the way I think about mechanism design theory is, it's a benchmark. It's a wonderful thing to see how well we might do if we, sort of knew enough, but still taking into account at least some of the incentive constraints that we have. We might want to put in this incentive constraint if we could figure out how to do it well and so on. But at least it gives us a better benchmark than saying full first best efficiency. And, it gives us something to compare simple mechanisms like, a Dutch auction or a buyer's bid double auction and so on to see how well they do. So, now, if you go to the, I've been rereading some of the papers in preparing for this. It's a very interesting last sentence to McAfee and Rennie, where they basically said, gee, what does this literature on mechanism design with correlated values start saying? It starts saying, gee, incomplete information can't be terribly important. And, and why do they say it is, gee, you can get this, you can get full efficiency, you can get full surplus extraction. And then you see here where we go, and this is with correlated values, remember, you see this very rapid convergence. In other words, gee, except in really small markets, the incomplete information doesn't matter at all in a double auction. And I've written some papers with Schneer on markets which meet, over time. You can trade now, you can trade tomorrow, you can trade the day after, and as you make the market more liquid, in a sense, you can have an opportunity to trade more often. You get a similar type result. You go to efficiency, and the incomplete information doesn't much matter. Now that was with independent private values. I bet it works for correlated private values. I just don't know how to do it. Okay, that's enough. Thanks very much.